I think now it's time to move on to the challenge participants. So this first presentation will be given by Zeeshan Khan Suri. So if you're there, please unmute yourself and you can feel free to share your screen.
Hi, do you see my screen?
Yeah, we can see your screen and we can hear you. Okay,
Yes.
great. Thank you so much.
Hello, guys. My name is Zeeshan Khan Suri. So I work as a computer vision engineer at Denso Europe. So this is a part of Denso Group, which is a automobile parts manufacturer. And in our in Lindau, we work on computer vision and autonomous driving. So today I'm here to I'm here to present my contribution to this challenge. So as you can see here, so this method was scoring the second best according to the F score on the monocular depth estimation channel. So in order to motivate my contributions, I will start by a short recap of how monocular depth estimation is formulated during training. And here I start with a stereo setting as proposed by Garg et al. As you can see, if given a left image, we first predict an inverse depth using a depth network, and then since we already know the stereo baseline between the left and right image, so in this case for the kitty, this baseline between the left and right image was 54 centimeters in X direction. So since we already know this, we use this as the ego motion between the left and right image. And from the ego motion and from the depth estimate, we calculate a flow image, which here in this case is just in the X direction, as you can see on this flow image here. So this is just a horizontal shift in X direction with respect to the baseline between the left and right stereo images. So using this flow image, a warping is done of the right image onto the view of the left image, and then a loss is computed from the synthesized right image and the left image so that the gradients pass through the network and it produces correct depth. So from this stereo setting, what changes into a monocular setting, which was proposed by SFM learner, was so previously you had this known poses between the left and right image, as you can see here. So this ego motion was already known between the left and right images, but in a monocular setting, since we don't have a stereo setting, we are just using frames at different timestamps. And for this, you don't know the actual motion or the relative pose between these frames. So they introduce another network, pose estimation network, which takes in the consecutive frames and outputs an ego motion between them. So that is the main difference. That's mostly the only difference with respect to the stereo setting. And similarly, from the ego motion and the depth, a flow is computed. Here you can see that the flow is not only in X direction, but in different directions with respect to the motion of the camera. And this flow is used to warp the frame at time t+1 onto the frame at time t, and then a loss is computed. So the main idea of my submission comes from the following. So here in the stereo setting, we had already known the ego motion, so we didn't have to use the network. But my proposal is that let's say we also use the network for the left and right stereo case, and still estimate the ego motion between left and right image, and then do the rest as similar in the monocular case. So from this ego motion, estimate the flow, warp it, and calculate the loss with respect to the target image. And since we already know the motion between the left and right image, and so the motion is just a no rotation, only translation in X direction, because this stereo setup is rectified. So we can use this to supervise the output of the pose network. So the pose network takes in left and right image, outputs some estimation of ego motion, and then now we supervise this to be equal to the ground truth pose, which is in rotation is just an identity. That means there is no rotation and only a translation in X direction. So just with this simple additional loss, the network was trained similar to as you have seen from the benchmark from Jane. So additional details are that just as the benchmark proposes, we use the convex encoder and for the depth, and also for the pose network. So here, so in the benchmark, only the depth network had convex encoder, but we also proposed to use a convex encoder for the pose network. In addition, so compared to the Resonate 18 network. So except for that, everything is similar. And another additional thing is the proposed stereo post supervision loss, which has a weight of 0.1. So other thing is that we use a DiffNet decoder for the depth, which was also one of the method which the benchmark evaluates. So just with this simple setup, the following evaluation, you can see that this method improves with respect to the image metrics, the absolute relative error, RMSE, and mean absolute error. But with respect to the baseline, it lags behind with respect to the point cloud metrics, F-score, and so on. As mentioned by Jaim, this evaluation data set is completely out of distribution for the model, which was trained on Kitty's data set, which is a driving data set. And as you can see, all the methods here perform good on the driving scenes because it was trained on this Kitty data set, which is also driving, and not so. So the generalization is relatively worse to a new scenes. As you can see here, our generalization is a bit better than other methods. For example, in this tree as outlined here, our method doesn't have as many discontinuities in depth as the others. So in conclusion, so the main contribution of this work is to propose a stronger pose network and also supervise the pose network with the pose supervision. Since we already have this data, since we already know the baseline between the left and right image, which for Kitty dataset is 54 centimeters, we can directly use this to improve the pose network. And the main conclusion which can be made from this is that accurate pose is key for accurate depth, because this the pipeline is designed in such a way that if the gradients of the losses pass through both the pose and the depth network, and if your pose network is getting better, consecutively your depth network will also get better. So with that, I conclude this talk. If you have any questions, please feel to ask. Thank you.
Great, thank you. So do we have any questions from either the audience here or online? Otherwise, I can start with one. Yeah, it seems like a pretty interesting idea because a lot of times it's true that the pose network is kind of just forgotten about and just left in the background where a lot of times we don't even evaluate it. So you kind of don't really actually know what it's doing. So this seems like quite a simple but like clever way of reintegrating some of the supervision. I was wondering if you ever found that if you're only ever supervising it with one ground truth pose, does it ever collapse to just predict that same pose constantly, or is the rest of the supervision enough to kind of break that?
So I think the rest of because the weight of this supervision is quite less. So if let's say you have equal weights to other losses, then maybe this could dominate, but actually this is just one small loss and the other losses are on the image pixels. So for example, the number of pixels you have on the input image, those many losses you have there. So it hugely dominates this loss. But yeah, so I think in order to overcome that, we could, so for example, there were methods in WACV which also synthesize, let's say, intermediate images. Let's say you have image from time t+1, and you could also interpolate a frame in between those. Maybe you could also then estimate the pose between them and supervise with that. That could be other.
Cool. Yeah, thanks. That sounds like a cool idea too. So if there's no other questions, then we can thank the speaker again. Oh, actually, of course, as soon as I say that, another question appears in chat. So if you want, can you see the Zoom chat and read the question out loud, please?
Yes. So how well do you think the stereo pose supervision loss generalizes to other data sets? So does this need to be tuned for each data set? So yes, so because different data sets have different baselines, so the left and right image have different distance between them, and some data sets are not even rectified. That means there is not only change of pose in X direction, but also in like different orientation and different X and Y direction. So this could be generalized to data sets where you already know the pose between two different cameras, two different frames, and so on. So let's say this could even be generalized to monocular setting where you know the vehicle's pose, maybe from IMU or so on, and then you can use that as a additional supervision.
Cool. Well, thanks again. And yeah, now we have the final presentation from the workshop, which is the final Mono VIT team. So Xiaoxiang, if you're available, please again, unmute yourself and share your screen. And yeah, thanks again, Zeeshan.